Suppose f is a function from a to b, and r is an equivalence relation on a. We'll say f is compatible with the equivalence relation r if, for all x and y in the domain a, x related to y by r implies that f of x equals f of y. Okay, let's draw a picture. We have function from a to b, so here's my a and my b and f. Okay, so I'm just going to put maybe 3 elements in my b, and a has this equivalence relation r on it. And what I want to do is illustrate the equivalence classes. So let's suppose that there are 4 R equivalence classes in A. Okay, so we have maybe some elements up here which are all equivalent to each other via R, and some more here, and more here, and more down here. Okay, so 4 equivalence classes, and those equivalence classes are the elements of the set A modulo R, right? So A modulo R has this equivalence class as 1 element, 2 elements, 3 elements, 4 elements altogether. All right, now what does it mean for this function f to be compatible with this equivalence relation R? It means that for all x and y in A here, for all dots x and y here, if they're related by R, then they have the same image under the function f. Okay, so if you think about it, that means that these 3 points, all of which are related to each other by R, they all have to map to the same place over here. Okay, so maybe all these guys map to this element of B. All right, and maybe all these guys map to this element of B, and these guys to this one, and then maybe these guys map to the same thing that the previous one did. Okay, there's nothing that says that elements that are not related have to map to different things. It's just that everything here has to map to the same place, and everything here has to map to the same place, and they do. Okay, so this function f would be compatible with this equivalence relation R. So we're supposed to suppose we have such an example. We're supposed to prove there is a unique function h from the set A mod R of equivalence classes to B, such that for every x in A, h of its equivalence class equals f of x. Okay. Well, this kind of gives us a recipe right here for how to define h, right? H should take this equivalence class here to that element, and this equivalence class to that one, and both of these equivalence classes to that one. Okay, so actually these arrows are precisely the 4 ordered pairs in the function h. All right, so what's the confusion here? Well, I mean, what's not obvious about this? Well, notice that, I mean, f actually had a bunch more arrows in it, right? It had 1 arrow from this element x to here, and this element to here, and this element to here, whereas h just has a single arrow from this. Okay, so if this element here is x, then this here is the R equivalence class of x, right? And so h is mapping that over to here. Okay, and the other confusion is, well, we're not sure that we can actually define a function this way, because what if we decided to represent this equivalence class by as the equivalence class of that element y, right? So same equivalence class, but my Adobe Reader's going crazy here. So, but in this case, we would be defining this to be f of y, right, instead of f of x. And that should concern us a little bit until we realize that, well, if these are the same equivalence class, then that means that x is related to y. And by our assumption that f is compatible with r, then we get that f of x equals f of y. So actually, we have a well-defined function. We've only defined h of this equivalence class to be a single element of b. Okay. All right, but there was quite a bit that went on there, so this is a good thing to actually write out a proof of. And it's a little bit involved. There are quite a few layers to it, but I think it's really good practice of a number of things. So let's dive right in. You can follow along on the right side here as we go. So we begin with the function f from a to b and an equivalence relation r on a, and we suppose, as the problem tells us to, that f is compatible with r. And we want to show that there exists a unique function h. So there exists a unique h from a mod r to b, such that for all x in a, h of the equivalence class of x equals f of x. All right. Well, first of all, we're showing that there exists a unique. So there's existence and there's uniqueness. And we can also write out the definition of f being compatible with r, which was given to us at the top of the problem here. So we're just copying that. And I claim that this uniqueness part is immediate because, so we're supposing we have a couple of functions I and j from a to b, which are both sort of candidates for this h, right? And they both satisfy this condition, or this condition here, that when you apply them to the equivalence class of x, you get f of x. Okay, I and j both satisfy that. And so what that means is that for every input, I and j have exactly the same output, f of x. And we have a theorem we proved earlier that said that functions which always have the same value are actually the same function. Right? So they're the same sets of ordered pairs. So from that theorem, it immediately follows that I equals j. Okay, so let's not bother to write that out too much. And in the proof here, I just said, okay. Well, I came back to this a little bit later after defining my h, but I said uniqueness is going to be clear because a function is uniquely determined by its values. Okay. So, all right, so let's focus on existence. So here's where we need to actually specify some h, which we will define this way, and then show that for all x in a, this is true. Yeah, so, well, first of all, we have to show that h is indeed a function from a mod r to b, so that's the first line here, and then we have the rest of this on the second line. Okay, and so why am I defining h this way? Well, I want h to be to map the equivalence class of x to f of x, so it should certainly contain all these ordered pairs, right, for every x in a, and therefore for every equivalence class in a mod r. So let's make that definition and see if we can get it to work out. All right, now from that, we immediately get this thing, right? Because no matter what x is, this just means that if you have an input of x bracket r, you get an output of f of x, and you see that clearly from this statement here. So, I mean, okay, until we know that h is a function, this h of notation doesn't even make sense. So I guess what I'm saying is that once we've proven the function part, the first statement here, this will follow immediately from how we've defined h. Okay, so we still need now to prove that h is a function from a mod r to b. And we know what the definition of that is. For all, I'm using alpha here in a mod r. In the domain, there exists a unique b in the second set b, such that alpha b is an h. Okay, definition of h being a function. Now, you might wonder why I'm using alpha here. Well, you could, if you want, you could just say for all x bracket r in a mod r instead. Okay, instead of what I've written here, that would be okay as well. I just, for some reason, chose to do it this way. So let's see how it works out. Okay, so we will let alpha be an arbitrary element of a mod r, and we have another there exists a unique statement to prove. And then immediately, alpha being an a mod r means alpha is an equivalence class, is an r equivalence class of a. And so there exists some element x in a such that alpha is its equivalence class. Okay. And all right, there exists a unique. Break that up once again into existence and uniqueness. And over here, we can do an existential instantiation to get an x naught such that alpha is its equivalence class. And there we go, and we're out of space, so I believe we're going to take that bottom part and throw it up top here. And we'll first work on the existence. Okay, so if we take the definition of h and we use the fact that x naught is in a, then we know that we have a particular ordered pair with x naught in h. And I'm hoping that this will give us an element of b such that alpha b is in h. And indeed it does, because since x naught is in A and f is a function from A to B, the image of x naught is in B. And because the equivalence class of x naught is exactly what we're calling alpha, we can replace it by alpha here. And then these two statements give us what we wanted, right? Our B is this f of x naught, okay? And yeah, so we have A, B is in H as desired. Okay, so we have the uniqueness here as well. It's the last thing we have to prove for part A. So we will let C and D be arbitrary elements of B, and we will do direct proof. So suppose we have these two ordered pairs in H, and we got to show that C equals D. So I'll bring down some other givens we had from above. And then if these guys are elements of H, and we know what H is, right, then that means that in each case there exists an element of A such that alpha C can be written this way, or alpha D can be written this way. Okay, so I'll use U and V, and then we have the U's here and the V's here. And we'll do some existential instantiation to get what the ordered pairs are. And well, notice here, from this one we get alpha equals U naught bracket R, and from the second one we get alpha equals V naught bracket R. Those alphas are the same, and so these two equivalence classes must be the same as well. Okay. And if they're the same equivalence classes with respect to the relation R, then they are related by R. And now here's where we get to use that F is compatible with the relation, right? We can do a universal instantiation on U naught and V naught to get this conditional, and then we can bring down that C is f of U naught and D is f of V naught. Okay. And finally, doing a modus ponens, we get that f of U naught equals f of V naught, which together with those two tell us that C equals D. Okay. Whew. So that does it. That brings us all the way down to here. We did the proving existence, proving uniqueness, and eventually showed that C equals D. All right. So after I made all this up, I had second thoughts about using the alpha here. If I were going to do it again, I probably would just start off with, saying for all x bracket R in A mod R. That might simplify things a bit, but there's a good reminder that, what does it mean for alpha to be in A mod R? It means that there exists some x naught in A such that alpha is the equivalence class of that x naught. Okay, part B, quite a bit quicker. It's kind of the other direction from A in a way. Suppose this time that we have a function h from A mod R to B, and that for all x in A, h is defined to basically do the same thing f does, but to equivalence classes instead of just elements. And I want to prove that f is compatible with R in this case. Okay, so f is basically, we're putting a restriction on f here. We're saying that what it does to an element, it kind of is going to have to do to every other element in that equivalence class, right? Because it's just kind of following the lead of h, and h does the same thing on an entire equivalence class. All right, so let's write that out. We have these givens, and then in part B we have these new givens. Got to prove f is compatible with R, and when faced with new language, first thing to do is just write out the definition in terms of something more familiar. So that came from the top of the problem here. Let x and y be arbitrary elements of A, and suppose that x are y, we show that f of x equals f of y. Okay. And so we got to figure out how to use the given somehow, and the answer is we're going to do two universal instantiations, one for x, one for y, to get those two statements. Right. So as I was sort of hinting at, okay, f of x has to be h of its equivalence class, f of y, right, has to be h of its equivalence class, and guess what? Those equivalence classes are the same thing because x and y are related by R. So we know that their equivalence classes are the same. And if you just hit both sides of that equation with h, right, then you get h of x bracket R equals h of y bracket R. And those guys are just f of x and f of y. Okay, so you get that f of x equals f of y. If you want a little bit more detail here in the proof, I said, okay, by assumption, those were our instantiations. Because these are related, their equivalence classes are the same. multiply h to each side, you get this equality, and then this one's f of x, this one's f of y from up above, and so we get f of x equals f of y, and we're done.